Earlier in the year, remember when we started talking about antiderivatives and how to find them? One of the things we did was we took like a polynomial function like x cubed, and we thought, well, how do we find the derivative of x cubed? So we take the 3 and we bring it out to the front so that it becomes 3x cubed, and then we reduce the exponent by 1 so it becomes 3x squared. And we realized that if we wanted to find the antiderivative of 3x squared, we just need to do those steps in the reverse order, so that anytime we saw a polynomial term, we could figure out how to find the antiderivative of it. We basically did the same thing with sine and cosine functions. We didn't make such a big deal of it at the time. But what we're going to do now is we're going to take a look at something else that we figured out how to take the derivative of back in the first semester. And we're going to realize what kind of patterns we can recognize to find the antiderivative of a slightly wider bunch of functions than what we have at this point. So let's take a look at what I am talking about. All right, so we're here on page 599 of the notes. And so what they want us to do is they want us to find the derivative of these functions, and then they want us to, well, the integral of the antiderivative of a function, we know from the fundamental theorem of calculus that that's just basically where we started off with. But let's go through those steps. All right, so if we needed to find the derivative of sine 3x, how did we do that? That's a complicated function. I know how to find the derivative of sine of x, but 3 of x was sticking a function inside that function. So what was the process we used to figure that out? Do you remember which rule it was? It wasn't the product rule, because we're not multiplying these things together. We're definitely not dividing them. We've got a function inside a function. We're composing functions. And so to find the derivative of that, we used what was called the chain rule. All right, and so we thought here about what the inside function was and what the outside function was. So the function inside, the one that we calculate first, is we calculate 3 times x of something. So we're tripling the value there. And then we take the answer to that and we plug it into our outside function, which is finding the sine of whatever the output from g of x was. Do you remember how we found the derivative of this? Well, what we did was, and I'll put the rule down here at the bottom, they say anti-differentiation by pattern recognition. So the first thing they did is they wanted us to identify what we called the chain rule back in the fall semester. And so here's the rule of where you find the chain rule on our derivatives and limits reference sheet. And remember, the rule was that we took the derivative of the outside function, but instead of using x as our argument, we used the inside function, kind of just like it was. And then we couldn't just leave it like that. We needed to multiply by the derivative of the inside function as well. All right, so thinking about that, what's the derivative of our outside function? What's the derivative of sine x? Well, it's cosine x, but we don't write cosine of x. We're going to write cosine of 3x. Just like 3x is the inside of this function, 3x is going to be the inside of the derivative function. And we need to multiply this by the derivative of the inside function. All right, so that's the derivative of 3x, which is just 3. And maybe just to keep it pretty, I'm going to put the 3 out in front like that. All right, and so obviously, if we took the antiderivative of this, the antiderivative of the derivative of a function is just getting back to where we were, sine of 3x plus our constant. So if we wanted to find the antiderivative of something that looked like this, here's what our answer would be. Let's take a look at these other examples. All right, so here, once again, we've got our inside function and our outside function. So identify those. What's our inside? Our inside function is g of x, and our outside function, which we calculate second, is f of x. So g of x, the first thing we calculate here, given x as our input, is the cosine of x. And then when we have the result from that, we feed it into the outside function, which is taking the exponential of a function. So if we wanted to find the derivative of this complex thing using the chain rule, we've got the outside function, which is e to the x, but instead of writing e to the x, we're going to write e to the cosine x. Because remember, the nice thing about e to the x is it's its own derivative. And we need to multiply this by the derivative of cosine. So remember or look up what the derivative of cosine is. That's negative sine. And once again, I'll put that out in front. So sine x times e to the cosine x. And once again, if we took the integral of this, obviously, we'd want to get back to where we started. All right, here's another example. So once again, this time, the function we calculate first, the inside function, excuse me, is x squared plus 3. And then we feed that function into the natural logarithm of x. So what is the derivative of the natural logarithm of x? Derivative of the natural logarithm of x is 1 over x, but instead of writing 1 over x, we're going to write 1 over x squared plus 3. And then we're going to multiply that by the derivative of x squared plus 3, which is 2x. And very often, you'll just see this written as a fractions, 2x over x squared plus 3. And so once again, this is a new kind of function that we can recognize and find the derivative of easily if we recognize this pattern, that it's a function in the denominator, a polynomial in the denominator, or some other thing in the denominator, and then its derivative in the numerator. And so if we see that, that's going to be the natural logarithm of the thing that's in the denominator. And the last thing that we'll look at here is f of x is equal to x squared plus 3. So once again, our outside function, I'm calling these g of x and f of x, even though all of these functions are called f of x, so I apologize for that. I'm hoping you're picking up on what I'm saying from context though. So first thing we're doing is we're taking x squared plus 3, and then the output of that, we want to find the square root of it, which I'll write as x to the 1/2 power, because this is what really reminds us of what the derivative of that is going to be. So the derivative of that is 1/2 times x to the negative 1/2 power. Okay, and so I'm going to have 1/2, and then the x to the negative 1/2 power would be, move the x to the 1/2 down to the denominator, and then write that as the square root of x again. And again, I'm going to say x squared plus 3, and then we multiply that by the derivative of x squared plus 3, which is again 2x. So that's equal to 2x over 2 times the square root of x squared plus 3. And we'd probably cancel out these 2 x's. So once again, we can kind of see a pattern here, that if I've got the square root of some function in the denominator, and then something kind of looking like its derivative in the numerator, that could give me a clue of how to take the antiderivative of it, x squared plus 3 plus c. All right, and so here's the idea that once again, we've got the chain rule here, that the derivative of f of g of x is equal to f prime of g of x times g prime of x. And so if we want to take the antiderivative of a function that's in this form, the fundamental theorem of calculus tells us that it's just f of g of x plus c. All right, so this was kind of a long video just because we were going through 4 examples of it. But in the next video, what I want to start doing is to start looking at a set of rules called U substitution that's going to let us find these things if we're starting from the middle, if we're starting from a function where we can find the antiderivative by using this technique, and then we'll see what that looks like in a whole bunch of different examples.